In this video we're going to calculate the standard errors for B and the t-tests related to the coefficients B. To calculate the standard error of the B coefficients, we must have the standard error of regression, which I will put right here. The standard error of regression is equal to the square root of the mean square error, or 323. The standard errors for the B's, which will go here, are calculated using the standard error of regression and the main diagonal values in x prime x inverse. The first standard error value is equal to standard error times the square root of the main diagonal entry here. And when I hit enter, I get a standard error of 1.4. Similarly, the standard error here, which is the standard error for the coefficient on visibility, is equal to the standard error of regression times the square root of the main diagonal entry here, which is the entry that corresponds to visibility. When I hit enter, I get a standard error of 11.6. And finally, although we are not particularly interested in the t-test for the intercept, we will get the standard error of the intercept, which is equal to, again, the standard error of regression times the square root of this entry. These are the main diagonal entries in the x prime x inverse matrix, and we get a standard error of 435. So now the t-test is simply equal the value of the coefficient for size of the hospital divided by the standard error, and we can drag this down, and we have the t-test for each of the coefficients, and finally the probability of those t-tests. This is equal to t-dist with the absolute value of the t, degrees of freedom equal to the degrees of freedom in the air, and it is always a two-tailed test. So the probability of that t value is 0.035. Now if I fix the degrees of freedom, I can drag this down and get the probability for each of the t-tests. And we can see that both size and visibility of consequences are significant predictors of total charges. Finally, I'll get the r hat 2 or r square for this regression analysis. It is equal to the regression sums of squares divided by total sums of squares, or 0.69.